Hey folks, welcome out there. Hi, it's TNLearn Mathline. You hear the music, you know exactly where you are. I'm Ernie Roberts, I'm your host for this afternoon's session, and I want to thank each of you for tuning in this afternoon. We have a great show for you. It's not a call-in day, all right? We will resume that. We're not going to presume anything. We're going to resume it next week. We'll be back on Monday through Friday with the live call-in shows. But today, it's all about a topic. What kind of topic? Well, hey, I'm all about finding out. Let's check it out and see what we've got going on here today. Practice with the parallelograms. Practice with the parallelograms. So we're going to look at some problems that involve various types of parallelograms, all right? And what we're going to do, like I said, it's not a call-in day, but what we ask you to do, get your pencil, get your paper, you might need a calculator, all of those good things, and let's sit back, relax, have a little bit of fun, and learn a little bit of math today, all right? Maybe challenging, hey, maybe not so much. But some of you are on the review moment. Some of you are saying, what's a parallelogram, all right? Because I'm sure we got viewers on all different levels here. So let's take some practice on it, and I'll talk you through and review you a little bit along the way, also get you up to speed, all right? Let's see our first problem, see what we've got going on here. Here we go, parallelogram. So first of all, everybody says, what's a parallelogram? It is a four-sided figure, that's a quadrilateral, and it has opposite sides. Now I'm going to mark those. Hope that marked. Oh, that marked very nicely. There we go. And those are parallel. That means they don't intersect. They stay the same distance apart. A lot of ways you can look at it. By definition, they're two coplanar lines that do not intersect. And these are actually segments, parts of those lines, okay? How about it? We've got another pair. We've got to have two pairs to make a parallelogram. So here we go. Kind of on the right diagonal up there. And here we go, the left diagonal, but they're running parallel also. And notice I use these little tick marks. They've got little arrows, all right? They're telling me, hey, parallels, going on and on. Now, when that happens, these opposite sides also become congruent. That means they have the same length. So we're talking about DE and CF having the same length, as well as DC and EF. Now, if you'll notice, DC and EF look a little smaller, a little shorter than DE and CF. That's okay. That's okay. They don't all four sides have to be congruent, but certainly by pairs. The opposite sides, this pair that I'm pointing at, the ones that are going on the diagonal, they've got to be parallel, as do the ones who are running horizontally there at the top and bottom of your figure doing so. Now feel free to write this figure down, all right? But let's see what we're going to do. It says we're going to find the value of y, which means we're going to solve for y. We're going to check also. Everybody says we're going to check. We're going to check. That's the important part. And we've been given a couple of conditions here. We're told what cx and xe have for measures, okay? Lengths, they may be feet, they may be inches. They're basically an algebraic expression, all right, here. We're going to try to find the value of y that makes or happens or makes this a true situation given we got a parallelogram, all right? So we got this parallelogram, CDEF. So you say, Ernie, what are we going to do with those diagonals? Because we've already talked about a lot of things being congruent. There are a few more pieces that are congruent. Now, the whole diagonals are not congruent in this picture. I think you can see that it looks like CE might have a little bit longer than DF. So that's not true. They're not the same measure. They do intersect each other. They do come together. And there's something important about that x right there. That's why we brought this problem involving CX, which means distance from C to X, point C to point X, and X to E. Now, my figure's a pretty good parallelogram. It really is. And if you draw a good parallelogram, a lot of these rules, these qualities will shine through. And this is a good property about these diagonals. The diagonals are not congruent. No, don't go there. But what they do in working together is they bisect each other, all right? So we're going to pick up, we can say dx is congruent to xf. Notice I put two ticks on there. And then on these other guys, since they're a little different, let's put one tick on them, all right? And that's our measurement ticks. They're not arrows per se because they're not running parallels here, all right? We're just saying cx has the same measure as xe. That just gave us a nice hint. So I'm going to write it down here again. Remember what I said? The length of cx equals xe. That's going to get us going. That's going to get us started. You say, Ernie, how do we know that again? Because the diagonals of any parallelogram will bisect each other. And bisect means you get two congruent parts. In this case, two congruent segments which have equal lengths. Nice story, right? Are you still with me out there? Everybody is. I know, I know. So what we're going to do, we're going to take this little value. You see that little value? It's 5y plus 3. We're going to put it in place of cx. There we are, 5y plus 3. How happy together they are. Now, on the other side of the coin, xe, well, hey, we know it's 7. We know that it's 7. And that's our story right now. That's our story. That's all we know. And that's how we're going to, that's all we need to know to find out what y is equal, okay? What y equals to. So let's go after it. Algebra 1, pre-algebra even, all right? This equation is going to move really nice, sweet, and swift. So we're going to remove the 3 right there because we want y by itself. See, we do a little geometry. Then we fuse in our algebra. That's why you take algebra 1 before you take geometry in most places. Now, sometimes we get this integrated math class, and a lot of you out there are going to be in high school integrated math, where they basically fuse the algebra and the geometry together. But you've got to know that algebra part before you can apply it to the geometry, all right? So it still mixes in, but the algebra still gets a precedence, usually even in integrated math classes, all right? Now, speaking of which, I digress. I know y'all say, Ernie, get back to the problem. Ernie's getting back to the problem, okay? I got 5y there on the left-hand side, and I've got 7 minus 3 on the right, which gives me 4. Now, some of you are going like, Ernie, you're going to try to divide? Yeah, I am. Let's do it. Let's go for it. We're going to divide both sides by 5. And I know 5 doesn't go into 4 evenly. Well, it does if you put a decimal up there, but it doesn't even go up there one time, does it? So we're just going to let y equal 4/5. 4/5. You said, wow, that's interesting. Some of you like the decimal form. How about it? 8/10, or as we affectionately love to call it, 0.8. All right, but that means 8/10, which is the same as 4/5. All right. You say, will it work? All right, well, the big proof here is I'm going to take 5 times, I'm going to put 4/5 in there. You all know I love fractions. We're going to stay with it. We're going to add 3, and the question is, does it give us lucky 7? I think it will because we worked it out right, correct? Well, let's find out. Put a 1 under that 5 right there, and you can lose your 5s real quickly here. How quick? That's why we use fractions, because they really many times will just cancel out beautifully. And this is where it happens. I've got 4 plus 3. Everybody with me? Say yes, it checks. We have lucky 7 on both sides. So that's using the thought. We have to know our properties. We have to know our properties, what's going on. And when you look at this, notice what's involved. CX, XE, that's your pieces of information. You don't have any other information to play with, all right, except there's a diagonal going on there. But you do know with the parallelogram that is important information, what they do, how they work together. Those two pieces are equal to each other because diagonals bisect each other. Then you saw for the y, little algebra. Wow, geometry and algebra. That's why I love both those subjects. Love both those subjects. Hey, let's go ahead and get to another one here in just a second, all right? Now, like I said, parallelograms, they come in different shapes and sizes. However, that parallelism is always going to be there. You're going to have 2 pairs of opposite sides parallel. Now, I said different shapes and sizes because you might have a rectangle, you might have a rhombus, or you might have a square. Now, rectangle, you see right angles happening. In the rhombus, well, you all of a sudden have all 4 sides congruent. Not necessarily right angles in that figure, although there will be some that pop up when the diagonals get together. And then the square has everything you'd ever want. It's got right angles, congruent sides, oh my goodness, and even congruent diagonals, all right? So let's take things one day at a time, one step at a time. Let's take a look at a rhombus problem here, okay? Let's see what we got. I have, if one diagonal of a rhombus is 16 feet and the other diagonal is 30 feet, find the perimeter. Wow. Now, some of you are like, well, that's 4 different sides. They are, but remember, it's a rhombus. So all 4 sides are congruent, all right? All 4 sides have the same length. So once you get one, you've got them all. And all you have to do is basically add them together, or you can multiply by 4. Get the perimeter, all right? Once you get one answer, you are in business. But let's see. Talking about diagonals. We don't have any diagonals in this picture, do we? Well, let's draw a couple in there. Let's see how good I can do these on a specialized segment show. All right, we're going to look for going right down the heart here. I hope that works. One pretty diagonal in place, yes. Oh, by the way, do you notice those are two congruent triangles? Wow, they're also isosceles triangles. Just a little point of reference. Let's keep working on this thing. Let's see what happens when I draw the other diagonal in. Goodness, my goodness. I'm on a roll today, folks. Get some great diagonals. Right there, what's happening? You say, well, it looks like they're perpendicular. If it's a rhombus, which it is, that's what we have going on here. We have right angles, which means these little guys, these four little triangles we've created here, are all right angles. And on top of that, they're all the same in congruence fashion. They're all congruent to each other. You could swing them around, you could rotate them, you could reflect them, you can put them right on top of each other. They will fit perfectly, all right, because that's what the diagonals of a rhombus do. They form four congruent triangles, and those are all right triangles. Now, the congruent triangle part, just a little bit of heads up to you. Like I said, we're reviewing today, going through a lot of things. But let's go back to the fact. We know the diagonals do what in a parallelogram? And a rhombus is a parallelogram, my friends. Oh, yes. Oh, yes, oh, yes, oh, yes. So the diagonals are bisecting each other. I gave you two great clues right there. Two great numbers to use in this picture. By the way, pictures are worth 1,000 words. Amen. All right? Definitely. You want to use a picture anytime you can. It will make problems so much easier to solve. So let's see what's going to happen. I have, looks like 16. This one looks smaller than that one. So I'm going to go with the shorter diagonal as being 16. So we're going to split it, 8 and 8. All right, everybody see that? We're also going to do the same thing for 30. We're going to split it now, a little bit bigger, but y'all can have it. Think about your money. $30, or just in this case, maybe 30 inches, 30 feet, whatever. It's going to be 15. 15, and there you go. Now the question is, where does that help us? How about it? I see two legs of a right triangle. If I have two legs, I can find the hypotenuse. Good old Pythagorean theorem will work for us. And let's see what we get. All right, so we're going to take 8 and we're going to square it. See that? That's your leg. A squared, by the way, those of you who've forgotten Pythagorean theorem, a squared plus b squared equals c squared. You say, what's a, b, and c? A is a leg, b is a leg. C is going to be our lovely hypotenuse out here. I'm going to call it C since we don't know it right now, okay? By the way, this is C, this is C, this is C. Same right triangle. We don't have to do this 4 times. We're just going to do it once, and then we'll quadruple our result. See what happens. So we've got it. 8 squared. We're going to add 15 squared, and we're going to get our hypotenuse squared. That's what we're going to try to figure out. Now, times tables. 8 times 8, you got that. You got that. 64. I hope you have 15 squared on the tip of your brain, all right? Not, it's back there somewhere. It's one of those numbers that we see an awful lot when we work with Pythagorean, we work with right triangles. The number 15 pops up a lot. 15 squared is 225. That's nice to know. That's nice to know. I personally think it's great to know your perfect squares. In other words, results when you have 1 squared, 2 squared, 3 squared, and so forth, all the way up to 20 squared. I really think that's not clutter. I think it's a good thing to have because it's less time you have to spend on the calculator, all right? And those are things that you know. A lot of them are already, your times tables up through 12. You already know those. So you've got to learn 13, 14, 15, 16, 17, 18, 19, and 20 squared is easy. It's always 400. So just a few notes there. So something for you to work on, something for you to learn on if you do not know those. All right, how about it? It's going to be c squared. We're going to find out what c squared is as I digress a little more. Adding together, I've got a 64 and a 225. Goodness, I can do that mentally. You can do that mentally because we don't have to deal with it, do we? It's just simply 289. That's what happens. There's no carrying to go. You can do that mentally. That addition is very easy. And then this is another reason why I say know your perfect squares up through 20 at least, because we got a square root. We got to work backwards. And actually, this is a nice little situation. This is a perfect square. 289 has its own nice integer square root. And we want the positive square root because we're talking about lengths of a triangle here. So let's see the square root of 289. Think, go, go, go. It is 17. And the square root of c squared is just c. So remember, our goal is to find out what is the number that c is standing for in this situation. Looks like it's 17. You say, Ernie, are we done? Close. That's one side. Remember, our question asked, what is the perimeter? What is the perimeter? That's where we're going. And it'll be 4 times 17, or add them all up. It's the same thing, right? Multiplication is just repeated addition. And I believe you're going to come up with 68. Now that could be inches, that could be feet. Depends on what units you started out in this situation, all right? So again, this becomes 17. There's 17, and there's 17. So quick review on that. Also, some of you are going like, Ernie, they taught us things called triples. You say, what's a triple? 8 squared plus 15 plus 17, that's a triple. It's a Pythagorean triple. And when you recognize those, and many of you do after you see them over and over again, you kind of keep saying, hey, there's no sense in me doing all this a squared, b squared, c squared stuff. I know those 3 numbers work together. That's another option. That's another option to solve it. And then you'd still have to 4 times 17 to get to 68 for your perimeter. How about it? That's fun. That's fun because you're using some of your algebra, you're using your geometry together here. Wow. You know, again, that's why we learn all these good things before you tackle geometry in the world of algebra. Let's take another rhombus problem here, all right? Let's see, and make sure, yeah, go ahead and drop my lower third out there, guys. Thank you. In this case, we got a little different switch. This time I've told you the perimeter of the rhombus is 40 inches. So I didn't give you the hypotenuse, but guess what? We can find that quick and easy. Yes, very easy to do that. Just divide it by 4, right? So let's go ahead and draw in the diagonals because it's talking about diagonals here. Yeah, let's do that. See if I can draw them good. Pump along there. Get it to the edge. All right, and we'll come back, go vertical. Let's see, I'm going to go this way. Y'all got it lined up at home? Some of you are drawing these, I hope. And there we go. There's our other diagonal. And again, it's a rhombus. A little bumpy moment there. Right there is our center of this rhombus, so to speak. And yes, we have right triangles once again. And yes, congruent sides. And yes, bisecting diagonals. Need I say any more? All right, so we've got a piece there. Let's put a little 2-ticker there. And we'll go 3-ticking on this one. And here's the story. The story says the perimeter is 40. Split it 4 ways. We can do that. Very easy. So put a 10, put a 10, put a 10, put a 10, all the way around it. Boom, boom, boom. There you go. Now, one diagonal has length of 10. Now, folks, diagonal goes from vertex to vertex. So that crosses the whole thing. So it's not 10 and 10 here. That wouldn't work anyway. Your hypotenuse has to be the longest side. So this is going to be split and go 5 and 5. We do not know, and I'm going to call it X. You can call it B if you like, or you call it A, whatever. I'm going to go with X there. That's the missing piece. We'll talk about what happens when we find the missing piece. Let's go for it. Pythagorean theorem, of course. Why not? So a squared plus, this time you know the hypotenuse, so be careful. Does it matter which one's A or B? No, as long as it's 5 and X there. Do not put 10 in for A or B. I see students do that a lot of times because they just honestly think it's always going to be a squared plus b squared equals c squared, and you're always looking for c. This is not the case. You're looking for a leg, here. So let's go to it. 5 squared plus, I'll call it x squared, equals our 10 squared. Again, this is nice where you know your good old perfect squares. All right, we got 25 going on there because that's 5 times 5. X squared, we'll find out what it is here in just a minute. And 10 times 10 goes 100. Lose the 25. This time we're going to subtract. Remember last problem we had? We were adding numbers because both of these were numbers that we could add. At this point, we're trying to get x by itself. All right? So here we go. We subtract off, say goodbye 25, pops up over here. We have x squared equals 75. Think of your money. Now, a couple of things here. We could go, if you're taking an ACT test or an SAT test or some sort of a test that has multiple choice questions, you might see a decimal form here because, folks, 75 ain't going to come out even. In fact, it's going to ramble on and on and on. We're going to give it to you in radical form here. All right, we're going to go for radical form. You say, what does that mean? It means we're going to see the square root symbol and a number underneath it. We're not going to worry about changing it on the calculator to a decimal. All right. So what we're going to look at, we're going to have to take square root of x squared because we want to know what x is. And we got to take the square root of 75. So we're going to simplify. We're going to take this down somewhat because 75 is kind of a little intimidating there. So I know this gives me x. And over here, I'm going to do a little bit of figuring, all right? And you can do this figuring step in your head mentally, all right? 75, I want a perfect square times a number in order to break this down. Now, if I don't have any perfect squares that will divide evenly into 75, this goes nowhere, all right? So in other words, the 4 doesn't help me, 9 doesn't help me, but I see 25 because I think money. That's like 3/4. So I can put 25 times 3 out there. You see that? Because 25 times 3 is 75. I also notice, because I know my perfect squares, I know that 25 is 5 times 5. So that is perfect. I'm going to take the root to the outside, which is going to become 5. Root of 25 is 5. The perfect comes out. The imperfect, the root of 3, cannot be simplified. It stays behind. And there is my final expression. We can call that 5 roots of 3, just like we used to call 5x, 5x. But what does it also represent? It says 5 times the value of the square root of 3. So that is half a diagonal. Did y'all notice I said half a diagonal? That means this guy down here is also 5 roots of 3. And we put them together. We're going to say the diagonal equals 10 times the square root of 3, or 10 roots of 3. That's the entire length, because we double the 5, but not the root of 3. All right, we just simply multiply 2 times 5, we're done. It's like adding 5 and 5, we get 10, and we keep the square root of 3. Remember that, it's just like an x or like a y, and that's how it works, all right? So there's our second rhombus situation, all right, where we have to look for missing diagonal. And it's not that hard if you just remember some of the good things you've got going. Now, let's take a look at this last problem, because I think it's about all we're going to have. This is a square, all right? Looks at a square. And we've got the length of a diagonal is 10. Well, you say, Ernie, there's not a diagonal in the picture. All we need is 1. All we need is 1. So let's put a diagonal in there. As I swing this thing around, love this little triangle. And let's see what we've got going. We have a diagonal, honestly. Yeah, there it goes. There it goes. And we have we got 2 right triangles, because remember, it's a square. So we got right angles here, right angles there. Here a right angle, there a right angle, everywhere a right angle. Actually, there are 4 of them. And if we drew another diagonal, we'd have 4 more, all right? But we're not going to need to do that, because all it says here with the length of one diagonal is 10. Let's put that 10 right there. Now, another thing, a square, remember, these have the same length. Oh, we got a right triangle. Isosceles right triangle, in fact. That's what's so cool about this. Now, some of you go like, ooh, that's like a 45, 45, 90. The rule works there. It does. But some of you may not have done 45, 45, 90 degree triangles yet, and you're still working with this. Let's put an A right here and right there. We can work this out by using our good old buddy Pythagoras and his theorem, all right? And let's do it. We've got A squared plus A squared equals 10 squared. And he said, well, what happened to B? A and B are the same. Remember, these are congruent. These are congruent. So at this point, my goodness, let's do it. Did you ever think you were going to ever get to say 1 plus 1 again? Today is your day. Today's your day. It gives us 2a squared, because that's 1a squared plus another a squared. It's 2 of them. Now over here, we can do 10 squared. We know our perfect squares. Let's do it. How about it? We're going to get 100, right? 10 times 10, 100. Now, quickly divide by 2. And what that does for me, that gives me a squared equaling 50. Now be careful. We're going to square root, and it is so easy to think, oh, it's 25, because you think of taking half. You don't take half. We're looking for a number times itself that gives us 50. It's irrational. It's not going to work. So we got to do our little trick. We got A. Let's break that down. Hey, quarters again. 25 times 2. Break it down. A perfect square times the number. Square root of 25 equals 5. Pull out the root of 2. Pull out the 5, leave the root of 2. We want the length of the sides. Well, there they are. 5 roots of 2. Perimeter, how about it? 4 times 5 roots of 2. You got it. 20 roots of 2. Remember not to multiply that by the 4. Hey, folks, thanks for tuning in to Specialized Segments today. We're going to be back live next week with some good call-ins. We will see you next time.